The broad pitch of this talk today is that causal inference guides decision making, but not all questions can be answered with A/B testing, and causal impact analysis needs to be credible in any case. And it's somewhat a pitch for using CausalPy, a causal inference package in Python, which is developed on the back of PyMC, for both the quantification of uncertainty and the sensitivity analysis of treatment effects in causal inference. The broad agenda of this talk is going to be something akin to this. We'll talk briefly about being a data scientist in industry, the pressures to do inference right, causal inference credibility. We'll talk about instrument variable designs and propensity score designs, and we'll sort of conclude around uncertainty in the model and uncertainty about models. Preliminaries, I am a data scientist. I work for Personio. My name is Nathaniel Forde. You can find my website here. All the sort of examples we're going to be discussing today are sort of implemented already in CausalPy, and the docs will have worked examples with code. Cool. So broadly, if you've worked as a data scientist in industry before, you probably have heard of the 80-20 rule or other species of sort of satisficing, where you have to make a trade-off between the efforts required and the value of the job done. This is generally just a piece of project management work that you need to do, but there's a risk for too much satisficing in data science, I think in particular, that has an acute kind of risk for compounding effects of poor decisions. So one poor decision after another has a sort of uniquely compounding effect in, say, the science of measurement, because if your measurements are all proxies all the way down, by the time you get to a decisive decision point, you might be talking about garbage regardless of how well you apply your method at that point. The sort of thrust here is that like causal inference is going to be important going forward, more important perhaps than it ever was before. Directionally correct might have been good enough 10 years ago. It's not really going to be good enough in a sort of zero interest rate world where poor decisions are wasteful, in not just in effort but in money, and money is more of a premium today than it was 10 years ago. Industry in general, and data science industry in general, has like developed massively in terms of the sort of default ability to do good causal inference in industry. A/B testing platforms run the gamut of utilities. So you have like platforms like Statsig or EPO that are wonderful and fantastic for scaling experimentation in a company. They sort of generally apply a simple kind of A/B test style methodology for evaluating treatment effects. I'm just going to skip these down. And there is a challenge to this. So like, yes, the quality of decision in a business is improved as a basis of increased scalability of A/B testing, but not every question can be answered with an A/B test. Sometimes it's unethical to do so. Sometimes it's feared to be unprofitable, like significantly unprofitable, and the product managers just want to launch immediately. So the challenge for a data scientist working in industry, to my mind, is to how to sort of improve the broad decision quality in a company without necessarily, applying an A/B test for every point of decision. So like in a time-constrained and resource-bound environment, how can you put forward your best foot with quality causal inference practices? That's the challenge that I think we're faced with. So the broad idea here is that, so like you can collect data forever. You can run an A/B test for 2 years until you have enough data. And that was so that the question is blindingly obvious. But like in most cases, you're not going to be able to run the test for as long as you would like. And you need to have a fallback understanding of like what the data means, what the metrics that you're seeing means. So that generally means that you need to have an understanding of the data generating process. Which are the important variables in your processes? Which are the sort of levers that you can pull to improve the metrics you care about? And I want to suggest here that one way to go about this is to learn to do sort of causal modeling of your workflows or your metrics trees, or however you sort of conceptualize the metric space in which you work. you should have a sort of causal effect understanding of how each of the metrics influence one another. And that enables you to answer questions compellingly, even without being able to run an A/B test on the basis of them. And here's the sort of plug for CausalPy. CausalPy is a sort of Bayesian causal inference package primarily. It does incorporate sort of causal inference models or designs. They use scikit-learn as well, but it's primarily a sort of Bayesian inference, causal inference package. And one of the sort of main utilities of framing these causal questions in a Bayesian setting that I'm going to argue for is that it allows you to do sort of principled sort of model comparison practices and sensitivity analysis to sort of test the robustness of the treatment effects derived in your modeling. There's generally an extensive sort of revolution in the social sciences around the sort of credibility of the questions that can be addressed by social sciences, and it has come in the form of sort of tailoring designs or data gathering designs and analysis routines to particular questions and estimates. So like you try to frame your business problem in such a way that it corresponds to a model you can deploy. By model, I mean a sort of mathematical model. And you want as much commensurability between your mathematical model of the situation you're interested in and the situation at hand, so that you can kind of compellingly argue that the sort of coefficient weights or the treatment effects derived from your mathematical model correspond to the likely effects of such a policy intervention in the real world. Okay. And so we're going to talk about two types of sort of model or canonical designs today. One of them is being instrumental variables and the other being propensity score weighting techniques. So on the left here you see two DAGs. The top DAG is basically the DAG you would have for an A/B test, where or, the letter R here, is randomization to your treatment, which allows you to read off cleanly, or the argument goes, you're allowed to read off cleanly the treatment effect from the coefficient Z in the regression equation on the right-hand side. An IV design does not have the sort of benefit of the A/B test where you can put forward like a randomization routine to determine who's in the treatment control group and treatment control. Instead, it's a sort of jerry-rigged method where you use an instrumental variable, which is a proxy for randomization. So it's a measure that sort of induces a A/B testing-like scenario on the manner in which you read off the coefficients from your model. And I'll talk about one that's sort of famous in the literature. But first, this is how you implement the IV type design in CausalPy. You have your data, you put forward it into basically, not quite one line, but like it's basically one model object, which will give you your analysis routine and spit out all the appropriate coefficients with the relevant uncertainties. So the Bayesian way of modeling an IV regression, sorry, I should have said here, typically on the right-hand side at the bottom, typically when you model an instrumental variable design, you do two-stage least squares to estimate the coefficients. That is, you first build a model which predicts your treatment, your propensity to treatment in some sense, and then you use the predicted outcome from that first model to predict the outcome Y that you're interested in. And doing that two-step maneuver will get you a treatment effect that avoids the bias in your data generating process due to the confounder set X in that DAG on the left-hand side. So if you want to sort of model that in a Bayesian setting, you treat it somewhat seriously as a multivariate normal distribution for the treatment and the outcome variable. And what's interesting and maybe slightly different from sort of presentations you've seen of IV before is that you model that as a multivariate distribution and then you have explicitly modeled the covariance structure between these two outcomes, right? The treatment outcome and the outcome variable of interest. Okay. So for an example, we want to say estimate the effect. This is quite common in the literature. The effect of education on sort of wage outcomes for an individual. This is confounded by this sort of unknown basket of measures that we're bucketing here as ability. So ability determines in some sense your education, but it also likely determines your wage. And we need to configure a model so that we can cleanly pull out the isolated effect of education on wage growth. And to recover that sort of analysis, we're using, or rather I think CARD used initially, nearness to 2-year and 4-year colleges as an instrument. And the argument being that nearness or geographic nearness to a college is effectively random, or like a randomization routine on which education path you get to choose. And we can use this in our modeling to try and recover the treatment effect unbiased by the sort of correlations between ability and education. So on the left-hand side here, you see 2 graphs, which education on the x-axis, log wage on the right-hand side. And then we've colored the dots, these are individuals, by their prevalence, their nearness to college, yes or no, so red or blue. And nearness to 4-year colleges on the top sort of shows higher prevalence of blue people, will say, in the final outcome of log wage, and the general trend is more education leads to an increasing log wage. You see similarly below the same plot, but for nearness to 2-year colleges, where you then see a spike in attendance for the 15-year buckets, people who have achieved 15 years worth of education, say. So what this is sort of a visual check on the strength of our instrument, basically arguing that this instrument is relevant to the outcome we care about. It has some sort of driver effect on the log wage growth for these individuals via attendance to college. The natural comparison to test whether or not the degree of bias we've seen in an IV circumstance is to compare the treatment effect that you get from a simple OLS regression to the treatment effect that you get with an IV regression. And so the literature shows that the OLS regression is a very tight coefficient, that's the red plot on the bottom here, around 0.06. But the IV regression pulls out something closer to 0.12. Right. So it's a significant difference in the understanding of the impact of education on log wages. I'm not going to dwell too much on this because I think, can you remind me when I've like 5 minutes or something like that? Yeah, cool. So basically the challenge then when you're designing an IV design or an IV model to pull out these treatment effects is to understand and justify the instruments you're using. So we could have used a 2-year instrument or the 4-year instrument. Arguably, that's just a modeling choice. But we want to be able to test and validate that our model meets the minimum criteria for being an instrument. So there are canonical tests, like an F test to evaluate strength of instruments. But because we're in the Bayesian setting, we can also do sensitivity analysis on the strength of correlation between the treatment outcome and the outcome variable of interest. So we can pressure that question. We can strengthen our priors to say that there's a strong correlation between our outcomes or a weak correlation. And then see whether or not the data is sufficient to overwhelm these priors that we're placing in the model and robustly confirm the sort of 0.12 estimate of our treatment effect. So we basically compare multiple models configured with multiple different instruments and sort of different strength correlations on the priors that we push into this model. We can then do model comparison evaluations to test how robust is our treatment effect estimate and which is the sort of best understanding, which is the best instrument, which is the best understanding of the data generating process that we can kind of justify from the data we have at hand. We can then pull out these posterior predictive checks. I don't know if you're familiar with Bayesian modeling in general, but one good sort of sense check on whether or not a Bayesian model is well configured is if it can reproduce the observed data. So what you see on the right here is sort of the predicted posterior distribution and the observed distribution overlaid, and they're broadly well fit. And then at the bottom right here, you sort of see the marginal effects of setting education at 2 years, 10 years or whatever, and the rest at the mean value, and sort of pulling out what are the implications of this model. Okay, good. I know that was actually a lot. That was maybe more than I intended. I'll probably speak a little bit less about propensity designs but broadly the same structure holds here, right? We start with this ideal circumstance, which is the randomization routine, where we have an A/B test and we have pure randomization. A propensity score model attempts to recover circumstances similar to A/B testing, randomization, by reweighting our population in such a way as to weight them according to their probability of treatment. This is like a balancing act where we try to ensure that we have a representative group on the treatment arm and the non-treatment arm. If we start with observed data, we want to rebalance or reweight the data we have so that it promotes a fairer contrast and is better at recovering what would have been seen under a randomization circumstance. In code, it's again pretty tight. Like it's basically an inference class that you can use in the CausalPy library. It takes a propensity score model and it runs an inverse propensity score weighting routine, and will spit out a bunch of plots and a bunch of summary data. One thing to kind of note here about propensity score modeling in general that's useful to kind of flag is that the propensity score should reflect an individual's propensity to receive the treatment in the population, not just in the sample data that you have. If you overfit a propensity score model to your sample data, you will get perfect fit in such a way that there's basically zero propensity for the identified treatment group to fall into the non-treatment group. And that breaks the entire understanding of what a propensity for treatment is. It breaks your generalization ability. And so what you see here on the left is a propensity score model for different groups fit with a logistic regression model. So it gets worse and worse as predicting, the more narrow and narrow the group cuts get. On the right, we have a propensity score model fit with a BART model, so that's like a tree type model. So it's searched all the tree paths and it has sort of perfectly identified from our sample who is in the treatment group and who is in the control group. If you use the propensity score on the left here, your estimates will be skewed and wrong. So like as part of this modeling exercise, propensity score modeling in general, you have to place weight on what is a good representation of the propensity for treatment in the population in general, which means you have to have a good understanding of what is a good model of the propensity. Okay. Once you do have a propensity score, you get all these nice things for free though. Like you get sort of balancing of the covariate profiles. So on the left-hand side here, you see sort of a ECDF, so an empirical cumulative density function for a particular variable I think it's just variable x1 in this, in the raw treatment and control group. After you apply the propensity score weighting, we overlay them again. So these are the adjusted ECDFs, and we get nice clean overlap. So the covariates are balanced between the two groups, between the treatment and control groups, after reweighting. This is a visual of what the reweighting does to your observed data. So there's two reweighting methods here, one on the left and one on the right. The yellow and the blue histograms overlaid up and down are the raw observed histograms for the outcome variable. And then the gray overlaid ones is the reweighted outcome variable according to our propensity score model. Two different types of weighting effects yield two different types of treatment effects, one more accurate than the other in this case. In this case, I know for sure that the true treatment effect is 2, so the overlap weighting, so that's the one on the left-hand side for me, and right-hand side for you, sorry, is the correct weighting method to apply in this case. Okay, yeah. So that's sort of a whirlwind tour, I know, of CausalPy and sort of causal modeling in general. The thing I wanted to pull out that's common across these two examples is that the ideal is A/B testing. The ideal is randomization. Both of these methods come with a slew of decision points you need to make. So you need to model the propensity, you need to find a good instrument, you need to ensure that you have the right sort of correlation structures between the instrument and the outcome. You're making a host of assumptions in standard causal inference when you're 5 minutes. Perfect, that's fine. 15 minutes? Oh, wow, okay, I'm flying through it then. So you'll have plenty of time for questions. And so yes, so we have two methods, IV designs and propensity score designs. Both come with a slew of modeling choices you can make. And points of design that you can put pressure on. Whether that is the weighting methodology you use, or the instruments you use, or the sort of like model selection criteria you use at the end of the day. And what I want to kind of conclude on is this point that there is broad uncertainty in models in general. So causal inference is going to wrestle in general with uncertain consequences of the assumed data generating processes. Bayesian causal inference takes that uncertainty quantification very seriously. And prior sensitivity analysis further establishes the robustness of our estimates under uncertainty. It allows us to interrogate our data generating models in a really sort of surgical way. Like if we feel that one of the covariates in our model is sort of misspecified, we get to scale up our prior weights on that, scale them down, change them, pull them apart, pull them out of the model, put them back into the model, and really assess the robustness of the treatment effects derived in a kind of compelling way. Secondly, you also have, and I've spoken about this less today, but you also have certain uncertainty about the model. So there's like candidate model graphs that you could, like innumerable candidate model graphs you could go over. And like you want an informed view of what are the plausible model graphs or model architectures. So you're going to put your opinion into this modeling development process anyway. But additionally, in a Bayesian context, you can do model averaging, where you take multiple models that you all deem like indistinguishably plausible. You can stack them and do a model averaging and get a model average of the treatment effects over that. And kind of what I'm trying to advertise here is that CausalPy streamlines the development and deployment of these sort of causal analysis models, gives you the proper tools to assess their uncertainty and communicate the impact of policy changes. It facilitates model evaluation, comparison, and combination to build credible patterns of inference and justified approaches to critical decision making. And that's it.
Regarding the IV choice, so you know you had the distance from school or distance from a college as your IV. The problem with that IV that I would see is that that's also correlated to other hidden variables. So distance from college, it's a rurally biased variable, has parental attributes, environmental attributes, careers of parents, and also where people live influences how much they earn. So there's a lot going on there. So, how do you get around that problem?
I mean, I think that's a totally fair criticism. There's a bunch of assumptions that you sort of need to bake into your IV choice. This is like, this is not my IV choice. This is like from the literature. It's like one of the canonical examples of instrumental variable regression. It's a fair point that it's possibly not a perfect instrument. But this is kind of going to my broader point here. It's like your choice of instrument is never going to be perfect. You're looking for something to just pull apart the correlation effect of the sort of ability, in this case, driving on the x-axis, right? So if there is correlations between your choice of neighborhood and the other variables, you're just hoping they're weak enough that your instrument is the background correlations are weak enough and your instrument is strong enough in the direct case to distinguish the naive OLS estimate from a slightly more realistic IV estimate. And you're right to question and push on that instrument. It's not a perfect one, and I think it's been roundly debated in the literature anyway. But it kind of goes to my broader point here, is that your instrument is a choice of the model design. You're arguing that this is the most compelling instrument I have to hand. This is the clearest I can get on the treatment effect for education with the data that we have available. So like in some sense, like building a Bayesian model, all your models are arguments. That this is the closest model I have of the world, and this is the implications of that model. Come with me on this journey, and let's see if we can do better.
Thanks. Yes, just a follow-up on that. I mean, does anyone kind of go a bit further, and then they say, okay, that's their concern with this IV. So now they're going to look at, rural versus urban and the relationship between that and wage, and see if near college or not near college has any effect. And if it doesn't, then that seems a better IV maybe.
Yeah, certainly. So in some sense, the education on the literature on the effects of education is what you want to look at. Never one individual study. So I agree there. Like there's no, like, this is part of the literature that builds, and what you want to see is like a broad, like kind of, if you do a meta-analysis of effect size attributed to education across a host of IV designs or other causal inference methods, it's the positive effect that you want to see greater than OLS that will confirm your belief in the actual claim, not any individual IV study. And yes, that has been done a lot. In fact, education is probably the most studied IV question in econometrics in general. Yeah.
Next question. All right then, thank you.
There's one more there.
Oh, we have one. Sorry, I'm sorry.
Hi, thank you for the presentation. If possible, can you share the slides, please?
Yeah, the slides are on my website already, so if you...
Perfect. And question of presentation to the stakeholders. Given the assumptions, given the limitations, how would you present to the stakeholders, because they are non-statistical people and probably would not understand a lot about this? What is your guidance on the presentation, such as making a yes/no answer to them, and also perhaps statistical percentage brackets, such as 95% statistically significant, and even potentially provide a range on the answers, such that they can judge and design the next step of action. Thank you.
Yeah, certainly. So, I mean, in large part, you want to lean on visualization, if at all possible. IV designs are maybe the hardest sort of canonical causal inference design to present visualization or visual comparison for. But a lot of stakeholders I work with are sort of product managers who are very familiar with A/B testing. And for whatever reason, when the conversation occurs that like we choose not to run an A/B test because it's too resource intensive, or we want an answer, that is not reliant on 2 months worth of an experiment, the sort of follow-on that we kind of tend to do is like, is there any natural experiment or causal inference methodology we could apply to get at the same question? We're not going to promise them like this is your guaranteed answer, but we're going to apply an analysis routine, which everyone understands a broad analysis routine, that will try to distill the impact your change to the product has had. And like, so nice ones like our interrupted time series type methodologies or difference in differences designs, where you get like kind of clean-ish plots to communicate that effect with. There's no silver bullet for how to communicate with every stakeholder. It's probably an individualist journey, but like if you already have them on board to the point that they're interested in running an A/B test, they're kind of there with you as well. They want to understand what is the appropriate measure of the impact that they're driving in the business. And you can say, well, we can't run an A/B test on this, but we can run such and such an analysis routine. It comes with some limitations and assumptions. You don't need to necessarily bore them with all those details, but you will need to report out what the results of your analysis was at the end. And I think you can do that in a stakeholder-friendly fashion, maybe keyed to the individual at the time. But visualization is generally what I tend to lean on, and clean time series ones are the nicest for that, I think.
Any other questions? All right, then. Thank you.
Perfect.